So which of the following conditions guarantees that the left-oriented rectangular approximation, so that's the Riemann sum, where the left-hand point is where the height is at, or the left-hand side of the rectangle is where the height is a under the positive function, the interval a to b, so it's positive, so we know it's going to be up, up here somewhere. So we're going to always create rectangles that go up like that. On a to b is always an underestimate of the true area. In other words, the rectangle should always be, or at least for the most part, be underneath the function so that it's always underestimating. If the function is increasing, that looks something like, linear function like that, then the rectangles we would use are these. So the left side is what I'm hitting the function at. And you can see that in all of these things, the rectangles are below the function. And that would happen no matter how I would do the increasing. So increasing, still increasing here. If I create the rectangles, the left-hand side always is going to be used, and it's always going to be underneath the function. So that would actually guarantee it. We can prove it, though, if we go through the rest of them. If it's decreasing like this, the left-hand side used, well, that's always going to be actually over estimating the function. So the rectangles are always going to be too much. Concave up, well, concave up would look like this. And it's true that it's decreasing here, so this is going to overestimate if we use the rectangles, but this side here underestimates it. However, if you have mostly concave, so it'd be mostly decreasing. So concave up like this, this is concave up, and you can see here that the rectangles are going to be overestimated. So that doesn't guarantee it. So decreasing doesn't, and concave up doesn't. Concave down, the same idea, whichever one would be it. So in this case, if we do it like this, this is concave down, but the rectangles are going to be, for the most part, overestimating it. So it's going to overestimate the function. And then the local maximum, that just means that it's concave, up and then concave down at some, or it's concave down on some point, some portion. I just actually showed that here. This one is going to be mostly overestimating it because this side is going to be overestimated for the vast majority of the interval. So the only way to guarantee it is if the function is always increasing.